All right, today we are diving into one of the biggest, most mind-bending questions in all of science. We're going to explore a truly radical new theory that might just solve a puzzle that's been around for a century, and it does it by suggesting that the very fabric of reality can, well, break. This is the central weirdness that gets everybody hooked on quantum physics in the first place, right? The universe seems to be playing by one set of rules when we're not watching, and then poof, it snaps to a completely different set of rules the moment we do. So why? What is it about just looking at something that forces reality to pick a side? So, before we can get to the incredible answer this new theory is proposing, we really need to get a solid handle on the problem itself. And it's a puzzle so deep, so fundamental, that physicists just call it the measurement problem. To get what this means, you have to imagine a quantum particle before anyone tries to measure it. Think of an electron. It isn't in one specific spot, no. Instead, it's in what's called a superposition, which is basically a ghostly cloud of all the places it could be, all at the exact same time. And right there, that's the big disconnect, isn't it? On one side, you have the quantum view of reality, this blurry, probabilistic wave of maybes. But on the other side, you've got the world we actually live in, a solid, definite reality, where your car is in the driveway, not in a haze of potential parking spots. How on earth does the universe get from A to B? This right here is the absolute heart of the measurement problem. What is the actual physical thing that happens that forces that haze of possibilities to just collapse and pick one single outcome, the very instant we interact with it? For almost 100 years, we've had no physical explanation for this. But that might be about to change. Okay, so the proposed solution starts by challenging one of our most basic assumptions about the universe. What if we've been thinking about space all wrong? What if the vacuum of space isn't actually empty? Get this. The core idea is that space-time itself has physical properties. It isn't a void. It's a substance. It's a medium with structure and stiffness, almost like a giant, invisible, and unbelievably rigid crystal that fills up the entire universe. The paper actually gives this cosmic fabric a name, a deep, glassy solid, or DGS for short. Now, this isn't something that exists in space, it is space. And just like any other material we know, it can be disturbed. It can be stretched, it can vibrate, and, this is the crucial part, it can reach a breaking point. Now, if you accept that space-time is a physical material, well, that changes literally everything. It means we might be able to take all the weird abstract ideas of quantum mechanics and translate them into real, tangible mechanical events happening in the fabric of space itself. So let's start with the wave function, that haze of possibilities. In this new model, it's not just a math equation anymore. It's a real, physical vibration, a ripple moving through that deep, glassy solid. Physicists actually have a word for a vibration traveling through a material like this, a phonon. So you can think of it like a sound wave, but instead of traveling through air, it's traveling through the very fabric of reality. So then, what's a particle? Like an electron? Well, it's not a tiny little dot. It's more like a stable, concentrated knot of that vibrational energy. It's a special kind of wave that holds its shape as it moves, instead of just spreading out. It's a little self-contained ripple in spacetime. And this leads to a really beautiful and honestly intuitive connection. The source material puts it perfectly. The mathematical probability of finding a particle in a certain spot simply corresponds to the physical strain energy in the fabric of space at that location. In other words, wherever the fabric of space is stretched and strained the most, that's where you're most likely to find the particle. Simple as that. Okay, we've laid all the groundwork. We've got our new picture of reality as a physical, vibrating substance. So now for the big payoff. Let's use this mechanical model to finally solve the measurement problem. What actually happens when we look at something? Think about it. Every material has a breaking point. You bend a paperclip, it springs back. You bend it too far, it stays bent. It fails. Well, this theory says space-time has a breaking point too. It's called the vacuum yield strength. And it's a fundamental constant of nature that marks the line where space stops behaving elastically, like a quantum wave, and starts failing permanently, like a classical object. And this gives us a beautifully clear mechanical role for why measurement causes collapse. If any interaction, what we call a measurement, stresses the fabric of space-time beyond this limit, the wave simply cannot be sustained anymore. It has to collapse. So let's just walk through it step by step. First, you've got a particle, just existing as a gentle vibration in space. Then, a detector comes along and interacts with it, applying a really sharp, concentrated stress. Third, that stress is too much. It exceeds the vacuum's breaking point. Fourth, the fabric of spacetime right there locally fails. And finally, in that instant of failure, the whole vibration collapses down into one single, definite location. The quantum mystery becomes a simple, cause-and-effect mechanical event. No magic necessary. But, a really great scientific theory doesn't just offer up a neat explanation for an old puzzle. It has to make new, testable predictions. It has to change how we see the world. So what are the real implications of an idea this big? And this theory absolutely makes concrete predictions we can actually go out and test. For one, it suggests that if we push spacetime almost to its breaking point in a particle accelerator, we should see tiny little effects that standard quantum theory doesn't predict. It also explains why big things aren't quantum. Their own mass puts too much strain on the spacetime fabric. And finally, and this is a big one, since collapse is a physical crack spreading through a material, it can't go faster than the speed of light, which would solve a lot of those spooky action at a distance paradoxes. But maybe the most profound takeaway is this. It completely unifies our picture of reality. It says there's no weird separate quantum world with its own rules over here and our familiar classical world over there. No, there is just one substance, spacetime, and it just has two different ways of reacting. It's elastic and quantum-like when you're gentle with it, and it's plastic and classical when you push it too hard. The source material really summarizes the entire incredible idea in one powerful statement. All the weirdness of quantum mechanics, that's just what it looks like when spacetime is behaving like a flexible, elastic material. And the mysterious act of measurement, that's just what we call it when we stretch that material past its breaking point. And that leaves us with a final, just awe-inspiring question to chew on. For a century, we've thought of space as just a passive, empty stage where the real action happens. But if this theory is right, if spacetime is an active, physical medium that can bend and vibrate and even break, what other incredible properties has it been hiding from us all this time? What else can the fabric of reality do?